Good evening, colleagues. Tonight we want to look at Bessel function. Now, Bessel function. Consider the Bessel equation of order n defined as s squared d square y dx square plus x dy dx plus s squared minus n y equals to 0. The series solution to this equation above are called Bessel function defined as Jn of x and j minus n of x. These two, Jn and j minus n, they are the linearly independent solution to the differential equation 1 above. We can use Frobenius method to solve this problem, and at the end of the day, we are going to get two linearly dependent solution, which is defined as my j of x and j minus n of x. Gn of x is defined as summation 0 to infinity of minus 1 raised to power n, x raised to power 2r plus n divided by 2 raised to power of 2r plus n, r factorial, the gamma of n plus r plus 1. While the one of j minus n is also defined as summation r from 0 to infinity r raised to power minus 1 raised to power r x raised to power 2r plus minus n divided by 2 raised to power 2r plus minus n r factorial, the gamma of minus n plus r plus 1. The two solutions are linearly independent. And also, one important thing that we must consider in Bessel function is that the power of x in your denominator must be the same as the power of 2 in your denominator. Let's see some property of the Bessel function Gn of x. Now, let's consider different values of n. The first case that we are going to consider is when my n is negative. When my n is negative, let's say, let n equals to minus p, then my Bessel function Gn will be defined as j of minus p, which is equals to summation from 0 r equals to 0 to infinity minus 1 raised to power r s raised to power 2r plus minus p divided by 2 raised to power of 2r plus minus p r factorial, the gamma of minus p plus r plus 1. If we let r to be equals to r plus p, then if we substitute it there, we are going to have minus 1 raised to power r plus p, x raised to power 2 into r plus p minus p divided by 2 raised to power 2 into r plus p plus minus p, the r plus p factorial, the gamma of minus p plus r plus p plus 1. At the end of the day, I'm going to have summation r from r equals to 0 to infinity minus 1 raised to power of r plus p x raised to power 2r plus p divided by 2 raised to power 2r plus p, the gamma of r plus p factorial, the gamma of r plus 1. One thing is we must make sure that the power of x in my numerator is the same with the power of x in my denominator. When we simplify further, I can bring out minus 1 raised to power p. Then I have summation from r equals to 0 to infinity minus 1 raised to power r x raised to power 2r plus p divided by 2 raised to power 2r plus p r plus p factorial, the gamma of r plus 1. We must maintain that same thing. The power of x and your power of 2 must be the same. At the end of the day, we notice that my r plus p factorial is the same thing as saying what? Gamma r plus p plus 1. And also, gamma r plus 1 is also the same as what? R factorial. If I substitute this, I'm going to have my what? My j of minus p, that is the Bessel function of minus p, will now be equals to minus 1 raised to power p summation r equals to 0 to infinity minus 1 raised to power of r x raised to power 2r plus p divided by 2 raised to power 2r plus p, r factorial, the gamma of r plus p plus 1, which is the same thing. That summation is the same thing as what? The Bessel function of what? Of p. Then if I substitute, I will now see that the Bessel function of minus p is equals to minus 1 raised to power p Bessel function of p, which is a very, very important definition. We should know this definition because it's very, very important. Now let's consider when my n is equals to 0. If n is equals to 0, if I substitute 0, then I will see that the Bessel function of minus 0 is also the same thing as what? Bessel function of 0. Now let's consider case 3 when my n is positive. If my n is positive integer, then I have let n equals to p, then we see that the Bessel function of p will be equals to minus 1 raised to power minus p, the Bessel function of minus p. Now, another thing we want to look at, which is very, very important, is the expansion of some special Bessel function, like Bessel function of 0, Bessel function of 1, Bessel function of 1 over 2, Bessel function of minus 1 over 2. Let's start with Bessel function of 0. Recall that the Bessel function of n is defined as this. Now, if I substitute n equals to 0, then I have Bessel function of 0 to be equals to summation r equals to 0 to infinity minus 1 raised to power r s raised to power 2r divided by 2 raised to power 2r r factorial, the gamma of r plus 1. At the end of the day, if I put my gamma of r plus 1 is going to give me what? R factorial. Then if I substitute, I have what? The Bessel function of 0 will now be equal to summation r equals to 0 to infinity minus 1 raised to power r x raised to power 2r, 2 raised to power 2r, the r factorial all square. Then if I express my series, then I'm going to have from 0 to infinity, my Bessel function of 0 will now be what? When r equals to 0, I have 1. When my r is equals to 1, I have minus s square over 2 raised to power 2, 1 factorial square. When r is equals to 2, then I have s raised to power 4 divided by 2 raised to power 4, 2 factorial all square. When r is equals to 3, I have s raised to power 6 divided by 2 raised to power 6, 3 factorial square. Continue like that. That is the expansion of what? The Bessel function of 0. Let's consider Bessel function of 1 and see what you are going to have. If you substitute 1 into the Bessel function of n, then we have this. Now, from indices, I can split s raised to power 2r plus 1, and also I can also split 2 raised to power 2r plus 1 to be s over 2 summation r from 0 to infinity of minus 1 raised to power r, s raised to power 2r, 2 raised to power 2r, r factorial, the gamma of what? r plus 2. Then at the end of the day, I will notice that the gamma of r plus 2 is sent as what? R plus 1 factorial. If I substitute that, then I can express the series now from 0 to infinity. When r is equals to 0, then I have 1. When r is equals to 1, I have s squared divided by 2 square, 1 factorial, 2 factorial, plus when r is equals to 2, I have s raised to power 4, 2 raised to power 4, 2 factorial, and 3. When r is equals to 3, I have s raised to power 6 divided by 2 raised to power 6, 3 factorial, and 4 factorial, and so on. That is the series expansion of what? Or that is the Bessel function for n equals to 1. Now, I want to look at the Bessel function for 1 over 2 and Bessel function for minus 1 over 2. But before that, we need to consider this. These two expansion is going to be useful to prove our Bessel function of 1 over 2, which is what? The Taylor series expansion of sine x and cos x. The Taylor series expansion of sine x is defined as x minus s cubed divided by 3 factorial plus s raised to power 5 divided by 5 factorial minus x raised to power 7 divided by 7 factorial. While the one of cos x is equals to 1 minus s squared divided by 2 factorial plus s raised to power 4 divided by 4 factorial minus s raised to power 6 divided by 6 factorial. Now, let's simplify our Bessel function of 1 over 2. Now, if I substitute 1 over 2 into my Bessel function of n, then I have this. I have summation r from 0 to infinity minus 1 raised to power r s raised to power 2r plus 1 over 2 divided by 2 raised to power 2r plus 1 over 2 r factorial the gamma of 3 over 2, which is equals. Now, if I apply indices to my x raised to power 2r plus 1 over 2 and also 2 raised to power 2r plus 1 over 2, then I can bring out square root of what? X over 2. Then I have this summation r from 0 to infinity minus 1 raised to power r s raised to power 2r 2r raised to 2 raised to power 2r r factorial gamma of r plus 3 over 2. If I express the series now, I have the square root of x divided by 2 into when when my r is equals to 0, I have 1 over gamma of 3 over 2 minus when r is equals to 1, I have s squared divided by 2 square 1 factorial gamma 5 over 2. When r is equals to 2, I have s raised to power 4 divided by 2 raised to power 4 2 factorial the gamma of 7 over 2. When r is equals to 3, I have minus s raised to power 6 divided by 2 raised to power 6 3 factorial r raised to power gamma of 9 over 2 and so on. Now let's now simplify. I can simplify those gamma. Now gamma 3 over 2 will be 1 over 2 gamma 1 over 2. My gamma 5 over 2 will be 3 over 2 times 1 over 2 gamma 1 over 2. Gamma 7 over 2 will be 5 over 2 times 3 over 2 times 1 over 2 gamma 1 over 2. Gamma 9 over 2 will be 7 over 2 5 over 2 3 over 2 times 1 over 2 gamma 1 over 2. We now see that gamma 1 over 2 is common. Then I can factorize out gamma 1 over 2. At the end of the day, I have my other series to be 1 divided by 1 over 2 minus s squared divided by 2 raised to power 2, 1 factorial, 3 over 2 times 1 over 2, plus s raised to power 4 divided by 2 raised to power 4, 2 factorial, 5 divided by 2 times 3 divided by 2 times 1 over 2, minus s raised to power 6 divided by 2 raised to power 6, 3 factorial, gamma, and 3 factorial, 7 over 2 times 5 over 2, 3 times 3 over 2 times 1 over 2. Now, gamma 1 over 2 is equals to root pi. Then if I substitute, I have my Bessel function of 1 over 2 will now be equals to square root of x divided by 2 pi into the other series. Then if I factorize, then I have the Bessel function of 1 over 2 to be equals to x divided by 2 pi. Then my 2 can go out. I have 2 divided by 1 factorial minus 2s squared 3 factorial plus 2s raised to power 4 5 factorial minus 2x raised to power 7 factorial. Then I want to make the powers of x to be of the same value with the factorial at the denominator. Then if I factorize out 2 and I multiply the whole expression by x, then I have the Bessel function of 1 over 2 to be equals to square root of x divided by 2 pi times 2 divided by x into x divided by 1 factorial minus s cubed divided by 3 factorial plus s raised to power 5 divided by 5 factorial minus s raised to power 7 divided by 7 factorial. If you look at the series, it resembles the word the Taylor series expansion of what sine x. Then I can easily substitute. Then I will see that the Bessel function of 1 over 2 is now equals to square root of 2 divided by pi x sine x. This is very, very important. Let us take note of it and know how to prove it very well. Now let's look at Bessel function of minus 1 over 2. Now we are going to follow the same procedure as for the Bessel function of 1 over 2. If I apply the same procedure, I will see that the Bessel function of minus 1 over 2 is going to be equals to square root of 2 divided by x into 1 minus s squared divided by 2 factorial plus s raised to power 4 divided by 4 factorial minus x raised to power 6 divided by 6 factorial plus continue like that. And this series look like what? Cosine, the Taylor series expansion of what? Cosine. Then the Bessel function of minus 1 over 2 will now define as square root of 2 divided by pi x cos x. Now let's look at some other important thing, which is the recursive relation of Bessel function. The first one we are going to look at is when we have the the derivative of x raised to power n times the Bessel function of n equals, we want to show that is equals to x raised to power n, the Bessel function of n minus 1. Now let's see. If I start from my left hand side, I multiply the Bessel function, I will multiply the Bessel function with what? X raised to power of n. When I multiply the Bessel function with x raised to power of n, I have summation from r to infinity minus 1 raised to power r, x raised to power 2n plus 2r divided by 2n plus 2r divided by n plus 2r, r factorial, the gamma of n plus r. Now, if I differentiate x raised to power n Bessel function of n, then I will end up having this. Then I know that the gamma function of r plus n plus r plus 1, instead of saying what? N plus r, the gamma function of what? N. If I substitute into it, I will now see that I can, from this numerator, I can bring out two I can bring out x raised to power n, because I have x raised to power 2n. If I bring one x raised to power n out, then I have x raised to power n into summation r from 0 to infinity minus 1 raised to power r. Then I have x raised to power n minus 1 plus 2r 2 raised to power n minus 1 plus 2r divided by the gamma function of n minus 1 plus r plus n times r factorial. At the end of the day, we now see this series is just in form of what? N minus 1, the Bessel function of what? N minus 1, because I can see n minus 1 at I have power x is having n minus 1 and 2 is also having n minus 1, which is equivalent to the Bessel function of what? N minus 1. Then I can conclude that the dx of x raised to power n, the Bessel function of n, is the same thing, is equals to x raised to power n, the Bessel function of n minus 1 x. That is the first recurrence formula. Let's look at the second one. I want to also show that the the derivative of x raised to power minus n of Bessel function of n is also equals to minus x raised to power n, the Bessel function of what? N plus 1. Then from here, let's see. From the general formula of the Bessel function, we have this. Then if I multiply through by x raised to power minus 1, we have this. Then if I differentiate, I have this. If I differentiate, I have this. Then I can bring out, since the power of x here, the power of x in my numerator is not having x, is not having n, and the power of x in my denominator is having n. Then for me to make the power to be the same, then I need to multiply my numerator by x raised to power. If I said multiply by x raised to power minus n, I can also add it to x raised to power 2r minus 1. Then I have this to be equals to minus, I have x raised to power minus n summation from r equals to 1 to what? To infinity, s r minus 1 raised to power r. Then x and 2, they are now having the same power. Then I have r minus 1 factorial n plus r plus 1. From here, I will put r equals to k plus 1, so that I can, now if I put r equals to k plus 1, then I have minus x raised to power n minus x raised to power minus n summation k from 0 to infinity minus 1 raised to power k x raised to power n plus 1 plus 2k divided by 2 raised to power n plus 1 plus 2k, k factorial, the gamma of what? N plus 1 plus k plus 1. At the end of the day, you will see that this series is just the same as saying what is Bessel function of what? N plus 1. Then if I multiply with it, minus x raised to power minus n, you will now see that the derivative of what? X raised to power minus n, Bessel function of n, is the same as what? Minus s raised to power minus n Bessel function of what? N plus 1. Let's see the third one. I want to show that the derivative of Bessel function of x is equals to n minus Bessel function of n minus 1 minus n divided by x Bessel function of n. Now let's see. From the recurrence formula, the first one we show, we have noticed that the derivative of the Bessel function of n, xn, Bessel function of n is defined as this. Then if I apply the same thing, then I can easily say what? S raised to power n, the Bessel function. If I differentiate this my left hand side using product rule, our normal product rule, then I hold s raised to power n, I differentiate the Bessel function, then I have jn factorial jn derivative of x plus, if I hold jn, the Bessel function of n, I differentiate xn, then I have this, everything equals to s raised to power n, the Bessel function of n minus 1. Then if I divide through by s raised to power n to make the coefficient of the derivative of Bessel function of n equals to 1, then I have n raised to power n divided by x Bessel function, and I collect like term. Bessel function of this will give me what? N raised to power x, n raised to power x, s raised to n raised to power n divided by s raised to power n times s raised to power minus 1, the Bessel function of n equals Bessel function of minus 1 x. Now, applying law of indices, my x raised to power n minus 1 plus 1 will give me what? S raised to power n. So at the end of the day, you now see that the Bessel function of n raised to power x is equals to what? The Bessel function of n minus 1. If I collect light, I make it to be the subject. Make Bessel function, the derivative of Bessel function of x to be the subject. At the end of the day, I have Bessel function of n minus 1x minus Bessel function of n divided by x, n divided by x, Bessel function of n. Let's look at the fourth one. We want to also show that what? The derivative of Bessel function of n is equals to minus Bessel function of n plus 1 plus n over x, Bessel function of n. The same thing, since we know the derivative of our Bessel function of x raised to power minus n from the second recursive relation I showed the other time, we now see, and which is defined as what? Minus s raised to power minus n, Bessel function of n plus 1. Now, if I use product rule to differentiate my left hand side, then I have, if I hold s raised to power minus 1 minus n, I have Bessel function of n prime minus, if I hold Bessel function of n, I differentiate s raised to power minus n, then I have this equals s raised to power minus s raised to power n Bessel function of n minus 1. Now, I want to make the coefficient of Bessel function of n prime, that is the derivative of Bessel function of n, to be 1, then I divide through by Bessel function x raised to power minus n, and after that I have this. Now, let's look at the fifth recursive relation. Now, we want to show that Bessel function of n prime is equals to 1 over 2 into Bessel function of n minus 1 minus Bessel function of n plus 1. If we combine recursive relation of 3 and 4, that is Bessel function, the 3 is Bessel function of n prime equals Bessel function of n plus 1 minus s raised to the power n Bessel function of nx. If I add it with Bessel function of n prime equals, which is relation 4, equals minus Bessel function of n plus 1 x plus n raised to power x Bessel function of nx. If I add it, at the end of the day, I will see that I'm going to have Bessel function of n prime equals 1 over 2 Bessel function of n minus 1 minus Bessel function of what? N plus 1. Lastly, let's see the sixth one, which is very, very important also. We want to show that 2n Bessel function of x is equals to x into Bessel function of n minus 1 plus Bessel function of what? N plus 1. If we subtract that same, we add for 5, we add relation 3 and 4. Now for 6, we want to subtract relation 3 from 4. Then if I subtract, I will see that I'm going to have 2 into n divided by x. The z function of x equals the z function of n minus 1 plus the z function of n plus 1. At the end of the day, I can multiply through by x. Then I have 2n. The same function of x equals x into the same function of n minus 1 x plus what? The same function of what? N plus 1. This last recurrence relation, this sixth one, is very, very important because that's what we are going to use to derive other derivative of the same function of fraction 1 over 2, 3 over 2, 5 over 2, and so on. Please take note of this last one very well. All others are also very important, but this sixth one is the most important out of it. Now let's look at example. We want to evaluate the z function of 3 over 2, the z function of minus 3 over 2, the z function of 5 over 2, and the z function of minus 5 over 2. I'm only going to do the z function of 3 over 2. That will employ you that you should try on your own. Try the same version of minus 3 over 2, the same version of 5 over 2, and the same version of minus 5 over 2. Last year, Dr. Ganil brought out the same function of 3 over 2. We don't know what will happen this year, but try as much as possible to understand this so that on your own, you can also solve for other derivative of it. Now, let's see the solution to it. From the recursive, I told you that there is recursive relation, the sixth one is very, very important. That is what we are going to apply here, which says what? 2 into n divided by x, the z function of n equals the z function of n minus 1 plus the z function of what? N plus 1. If my n is equals to 1 over 2, if I put n equals to 1 over 2, then 2 times 1 over 2 will go. We have 1 over x, the z function of 1 over 2 equals 1 over 2 minus 1, I'm going to have the z function of minus 1 over 2 plus 1 plus 1 over 2. I'm going to have the z function of 3 over 2, which is what we want to get. Now, if I collect like term, I'm going to have the z function of 3 over 2 equals 1 over x, the z function of 1 over 2x minus the z function of minus 1 over 2, which is very easy for me because I know the z function of 1 over 2 to be equals to square root of 2 divided by per x sine x, while the same function of minus 1 over 2 is equals to 2 divided by per x cos x. Then if I substitute, I will see that my Bayesian function of 3 over 2 will now be square root of 2 divided by per x into sine x over x minus cos x. Those are the solution to the question. You can use the same method to apply to get the one of what? Minus 3 over 2. If you want to do that, just say let your n equals to minus 1 over 2. Then you see that minus 3 over 2 will come out there. Also, if you want to do 5 over 2, you can let your n be equals to 3 over 2. By then, you will have known your 3 over 2 and minus 3 over 2. And after that, you can do the same thing for the other one. Please, on your own, try as much as possible to try them yourself. I pray to Almighty God to make this little effort of mine as an act of worship. Any error that I've in one way or the other committed, may Almighty God forgive me. And I pray this material will be useful for every one of us. Just accept the little one from me. Thank you very much.